Here's another problem to try. This time we're going to take a buffer solution using phenol, C6H5OH, and sodium phenolate, which becomes a source of conjugate base, and put those two into a solution and see what the pH is. And for this, we're going to be using the Henderson-Hasselbalch equation. Now, the first thing we want to do is just make sure that we actually have a buffer solution, even though the problem tells us that. Let's just verify that. And so we can write our acid dissociation for phenol, since we were given a Ka for phenol. That's an acid dissociation equilibrium constant. So we can write C6H5OH plus water. Remember, Ka is always an acid dissociating in water. It's an equilibrium with H3O plus. H2O takes that H plus, and then we're given C6H5O minus. And what also we see is we have the sodium phenolate, which is NaC6H5O. It is a sodium salt, and so sodium salts dissolve completely and completely dissociate, and that's going to leave us with C6H5O minus. And so we see that we have a source of that conjugate base from that sodium phenolate. So we have both the acid, the phenol, right here, and its conjugate base, the phenolate. And so that means that we do, in fact, have a buffer. We were given a Ka for that acid, and so our Ka is equal to 1.3 times 10 to the minus 10. When we are doing our Henderson-Hasselbalch equation, we will need the pKa, and so the pKa is going to be the negative log of that, and so the pKa turns out to be 9.89. So let's go ahead and set up our Henderson-Hasselbalch equation. So we have pH is equal to pKa plus the log. And we want to use our Ka equation here to do products over reactants. And so we're going to have the concentration of our product, C6H5O minus, my conjugate base, over my acid, which is C6H5OH, and that is my reactant. So we still have products over reactants. And so let's plug everything in and see what we get. So we've got pH is equal to the pKa, which is 9.89 plus the log. And we're going to do our concentrations. We have a 2-liter buffer solution. So in our conjugate base there, we're going to have 0.186 moles over 2 liters over concentration of our acid, which is 0.253 moles over 2 for the acid. And when we work all of that out, we get a value of 9.76 for the pH. Now notice here in our concentrations, we didn't really need to divide each of those moles by 2. Since we divided both of them by 2, those end up canceling out. We could have just used moles in place of concentration in that Henderson-Hasselbalch equation. It doesn't really matter which one you do, so whichever one you feel most comfortable with, that's what you should go with.